In this video, we'll look at how to calculate the total resistance if you have a group of resistors in some arrangement without having to build the circuit and actually measure the voltage and the current and divide and figure out the resistance of the group. There are rules for this, and we'll cover that in this video. So first, we have to explain what we mean by the total resistance of a group. The word we'll use is equivalent, the equivalent resistance of a group, meaning the group is equivalent or equal to a single resistor with a certain resistance. And that's what we're trying to find, is that resistance of what one resistor would have if it were exactly the same resistance as the group as a whole. So here's the situation. Pretend the group of resistors, whatever it looks like, is in a box and you can't see inside. And that box will have two connections. We can think of current going in, and charges going into the box and through one wire, and charges coming out. So every group we look at will be a two-terminal device, a device with two wires connected, one going in and one going out. No matter what's going on inside the box, there's always 2 points of connection. All right, here's the definition of what we mean by the total or equivalent resistance of the entire box. You put a voltage across the box like this and measure it with a voltmeter. That goes on top. And then you take an ammeter and you measure the current going into A and coming out B, either an ammeter here or an ammeter there. So just as in the little lab, you measure voltage across the whole thing, current through the whole thing, and you divide because V equals IR, and that gives you the resistance of the group. All right, here's a way to do that in an actual lab. You take your box, you connect it to a battery, nothing else in the circuit, and then you measure the voltage on the battery and the current coming through the battery because they'll be the same. There's nothing else. So the voltage on the battery is the same as the voltage on your group in the box, and the current through the battery is the same as the current through the group. So we measure those things, do our division. Okay? Voltage over current will equal the resistance, and that's the equivalent. We say that's the equivalent resistance of this group. So that's what the term means. The most common arrangements you'll see, and the only ones you have to really know for this class, is if resistors are in series or if they're in parallel, or some combination of series and parallel together. These are your two most common arrangements. First we'll look at series, and first we have to define what that means. It does not mean just that the resistors are in a row. And by the way, in case you've forgotten what a resistor is, I'll pause for a minute and remind you. Resistors look like this. Look like a little cylinder, and they usually have colored bands on them that tell us the resistance, and in 9th grade physics we'll learn how to read those bands so we can identify the resistance on a resistor. What they do is they maintain a constant resistance, a constant ratio between the voltage and the current, no matter what voltage or current you put on them in the ideal world. In your textbooks, they act like they have an absolutely perfect, fixed, constant resistance even if we put different voltages and currents on them. What would you use them for? They have a lot of uses. Basically, their general idea is that they control. They control the voltage or current in a circuit by maintaining a constant ratio between the two at that point. All right, so let's look at what it means for resistors to be in series. It does not mean that they're just in a row. These resistors are in series, but it's not enough for them just to be like in a row one after each other. What they have to do to be in series is they have to be in a row, and the same exact charges must go through the resistors in order for them to be labeled as being in series. Same exact charges. All right, so take a look at this first one, R1, R2, R3, and this is often how we label our resistors with a capital R and then a number. So that's resistor number 1. These resistors are in a row, and any charges that go through R1 have no escape. They have to go through R2 and R3. So we say all three of these are in series. These three resistors are in series. That's the expression we use. Now look at example B. You look at R4 and R5 and you might think, oh, they're in a row, so they're in series, but they are not, because the exact same charges won't go through both. Let's say the current through this one is 10. Well, there's a fork here, and some of those charges will go through this one. In fact, if these two resistors are identical resistance, 5 amps of current will go through this and 5 through this, so only half the charges will go through R5 that went through R4. So these are not in series. There are no resistors in example B that are in series. Not in series. Even though these are in a row, not every charge that goes through R4 will then go through R5. All right, now let's look at example C. Does every charge that goes through R7 have to go through R8? You can pause the video and answer that yourself. The answer is no because of this fork. So R7 and R8 are not in series. R8 and R10 are absolutely not in series. They're not in a row. But now look at R8 and R9. They're in this complicated arrangement, but does every charge that goes through R8 have to go through R9? Pause the video. The answer is yes. So in this arrangement, R8 and R9 are in series. And they're the only two that are in series in this example. All right, as I said earlier, your goal is to be able to predict the resistance of a group without having to actually build the circuit. There's a fairly simple rule for the total resistance or equivalent resistance of resistors in series. Take a guess. It's a very common sense rule. It's exactly what you want it to be. Let's say you have a 10, a 30, and a 20. Pause the video, take a guess. What do you think the total resistance would be for this group between A and B? And if your intuition said to just add them all up, you would be right. The total is 60 ohms. That's the total for this group. As you add more and more resistors, it's like adding friction, adding things that are sucking energy out of the charges as they go through. You're adding toll booths to take away money from these drivers. So if they go in a row like this, then they sum up and you get a total resistance like that. So pause the video and think, how would you write this in general if you had R1, R2, R3, and any number? What you would do is you would just write simply this, R1 plus R2 plus R3. How do you show that there could be 4 or 5 or 6 or 7? You write plus dot dot dot. So that's the rule for resistors in series. The other common arrangement, the second of two very common arrangements that you have to know for our course, is if resistors are in parallel. Parallel does not mean just geometrically parallel. It doesn't mean that. It means for the two elements, the two resistors, both of their tops are tied together and both of the bottoms are tied together. So let's look at these three examples. R1 and R2. Now it may be a little hard to see with the light, the evening light, but this R2 is in blue and R1 is in black ink. So let's see if they're in parallel. Geometrically they look like they're in parallel, but let's see if they're electrically in parallel. Okay, the top of R1 means the wire going into it that would bring current into it. That's this black line here. The top of R2 is that blue line. They are tied together at the top. Then look at their bottoms. This is the bottom wire on R1, the bottom wire on R2, and that black and that blue are tied together. So yes, these two are in parallel. All right, now let's look at these. Let's look at R3 and R5. Are their tops tied together? Look at the black wire coming off the top of R3 and the blue wire coming off the top of R5, and the answer is yes. So are these two in parallel? You may want to pause the video and answer that yourself. Are R3 and R5 in parallel? And the answer is no, because even though their tops are tied together, the bottoms are not. Here's the bottom of R3. That's that black line there. It is not tied to the bottom wire of R5. They're not tied together. There's the red resistor in the way here. So no, nothing in this circuit is in parallel. There's no two resistors where both their tops are tied together and their bottoms are tied to each other. Right, now let's look at C. Pause the video. Are these two in parallel or not? Right, well, they're not geometrically parallel. They're, in fact, they're perpendicular. If this is geometry class, these two are at right angles to each other, but it's not geometry class. We're asking if they are electrically parallel. So let's look, are their tops tied together? Black is tied to blue. Yes. Bottoms tied together. There's the bottom of R6. Here's the bottom of R7. This is wire, so tied all the way around. Yes. The bottom of R6 is tied to the bottom of R7. So these two are in parallel. All right. There's a rule for the total resistance of resistors in parallel, and it's a little trickier than the rule for series. After you learn it and go over it several times, it starts to become common sense and it's intuitive. And I have to break this into two parts because the 9th grade physics class only has to know what's above the line in black. What's below the line in blue, the AP class has to know. This equation is on the equation sheet. You have to understand it. This would only be bonus for 9th grade physics. So let's go back up to here. For 9th grade physics, we will only look at the case. We will limit ourselves to the case where the resistors are identical. So if the resistors are identical, and for those of you in AP Physics, you should pay a lot of attention to this because this is the most common situation and you want to be able to do these quickly. You don't want to have to take this kind of problem and go down here and plug this in and then solve it. That slows you down. All right, so let's look at guessing with actual numbers. Here's one resistor with a resistance of 12. Then we put two side by side, a 12 and a 12, and ask yourself, pause the video, what do you think the total resistance of this group would be? Now this is tricky because a lot of people want to write 24. That's absolutely incorrect. When you add resistors in parallel, put them side by side, you're actually making it easier for charges to go through. It's like starting with a one-lane highway and making it 2 lanes. So think what that does to the resistance. More traffic can flow. So did the resistance get smaller or did it get bigger? It got smaller, so this has to be a number smaller than 12. Well, how many times smaller did it get? So now, if you didn't get it right before, think of what would go in here. It has to be a number smaller than 12, and we doubled the width of the road. Another way of thinking about this is like one checkout lane at Target, and now we've opened 2 checkout lanes. So think what that does to the flow of traffic, and then think of what that did to the resistance. The answer here for the total resistance is 6. It makes it twice as easy to get through from here, from point A to point B. Twice as easy, which means the resistance is smaller by half, cut in half. Okay, following this pattern, predict what the resistance would be, the total resistance between point A and point B, if we put 3 resistors in parallel and each individual one has a resistance of 12. Right? You should get 4 ohms here. A single resistor in parallel, a single resistor would have a resistance of 12 here. And if you have 3 of them, it's 3 times easier to get through. You've cut the resistance by a factor of 3. You've divided it by 3. So it's 12 over 3. That's with specific numbers to build your intuition. But now let's talk about it in general. We need to do that with letters. So if n equals the number of resistors and r equals the resistance of just one of them, write in here what you think the formula would be based on these examples. What would be the formula for resistors in parallel if they're all the same? Okay? And I'll help you with that by looking at this one. In this one, R equals 12, N equals what? How many resistors are there? 2. And in this one, R equals 12 again. R is the resistance of just one of them. N equals how many are there? 3. So what do you do with 12 and 3 to get 4? What do you do with 12 and 2 to get 6? The answer is you take the resistance of one of them and you divide by how many there are. That's usually something you can do in your head. All right, for the AP class only, you would use this formula when the resistances are not identical in general for any circuit where the resistors are in parallel. And this is the rule. This is an unusual rule. It's not too hard to use if you have a calculator. You just plug in numbers and solve for what you want. But I want to say something about how unusual it is. It's a reciprocal rule, and you'll see more and more of those as you do more science and engineering. But in a reciprocal rule, you cannot solve this for the R parallel. You cannot solve this for the parallel R, this value here, until you know how many there are. So we can't rearrange this and rewrite it and solve it for that. If there were 2, we could. We'd do the common denominator, get both sides, and then do the reciprocal of both sides. If there are 3, we could do it. But if we don't know how many there are, if we want to write it in general, we have to leave it in this form. And then when we get a specific circuit and plug in numbers, then we can solve for this thing here. All right, and then finally, both classes, back to both classes, for both freshman and AP, you should be able to do some quick analysis when you have resistors in series and parallel. As usual, the series analysis is very easy and the parallel is a little trickier. For resistors in series, the total resistance is always, now I'm going to give you a multiple choice and you pause the video and tell me which one, or don't tell me, funny, you say to yourself which one you think it is. So for resistors in series, the total resistance is always what? Smaller than the smallest resistor, at the average of all of them, somewhere in between them but not the average, or bigger than the biggest resistance. Here's an example to help you with that. And when you look at what's the total resistance of this group in series, of course it's 106, so that tells you it's always greater than the biggest resistance. Because you look at any of them, start with the biggest, look at it, and think as I add resistors in series, I'm adding to the total resistance. So the total is always bigger than the biggest resistance. And that just makes a lot of sense. No one has any trouble with that. People have trouble with the next one. What about for resistors in parallel? If you have resistors in parallel, the total resistance is always what? Smaller than the smallest resistance? In between them somehow, in between the smallest and the biggest, the average of all three, or bigger than the biggest? You want to pause the video and think about it and see if you can get it right before I tell you. And the answer is it's always smaller than the smallest resistance. Almost no one gets this right the first time, but once you see the argument for it, I hope it makes sense and sticks in your brain. Here's why. Let's draw a circuit in parallel, and let's make this one pretty small, say 10 ohms, and then we'll put over here another resistor in parallel. We'll say that this is 1,000,000 ohms. All right, here's the thought process behind this. If you don't have the big one, if you just have that one, what's the resistance? It's 10 ohms. Now that's like having a pretty good highway, and cars are going along that highway. If you build another lane over here, it doesn't slow down the cars here. So all the cars are still going through this at the same speed. You still get the same current. Even if I build a horrible road over here, a dirt road with a speed limit of 1 mile per hour, it's still going to carry more traffic than this one would by itself, because I haven't actually changed this road at all. This is still just as easy to get through. So I still have all the same traffic going through the 10 ohm resistor. And by adding this, even if it's really, really big and only letting a little bit more traffic through, it's still creating more traffic than what we started with. So anytime you add anything in parallel, you reduce the overall resistance, because the original thing that was there is still doing what it was doing before. You haven't changed it at all. You've just added another root. Okay? All right, and then finally here's an example that you should be able to do on the homework when circuit arrangements are combined. Go ahead and see if you can fill in both blanks. Pause the video, and then we'll do it together. These two resistors are in what? They're in series, so their total resistance would be 20. These two resistors are in what? They're in parallel, and a 60 in parallel with a 60 is like a single what? It's like a single 30. So now this is like a 20 in series with a 30, right? These two by themselves are like a 30, and that creates a resistance here of 30. So now we have 10, 10, and 30. So that makes a total resistance of 50 ohms. That's a fairly straightforward problem, but we might take this arrangement and connect it to a battery. So here's the type of problem you want to work towards being able to solve. The question is, what's that current out of the battery if we connect the same circuit we had over here to a 100-volt battery? Now you could go through and try to solve it all and set up a system of equations or something like that, but you don't have to if you're looking at series and parallel. This 60 and this 60 is like a 30, right? That's what we already did. That 30 plus a 10 and a 10 in parallel is 50. So the total resistance here is 50 ohms. Between here and here, it's like you have a resistance of 50. You connect that up to a voltage of 100, and now you just use V equals IR, what's called Ohm's law, and you'll get that the current is 2 amps.